Welcome back to G Fun Facts Online. Today we are diving into a story that has been over 50 years in the making. It is a story about the fundamental laws of our universe, a wager made by a young physicist in a wheelchair, and a ripple in the fabric of space-time that finally proved him right. We are going to talk about the recent groundbreaking confirmation of Stephen Hawking's area theorem, an event that has shaken the physics world here in late 2025. If you follow science news, you might have seen the headlines about a signal called GW 250,114, but today we are going to move past the headlines. We are going to break down exactly what this means, how we managed to measure the unmeasurable, and why this specific confirmation bridges the gap between the gravity of stars and the thermodynamics of steam engines. Let's start with the prediction itself. The year was 1971. Stephen Hawking, then a young researcher at Cambridge, was working with the complex mathematics of general relativity. He derived a rule that was elegant in its simplicity but absolute in its implications. He stated that the surface area of a black hole's event horizon can never decrease. Now, let's pause and visualize that. The event horizon is that famous point of no return. It is the spherical shell around the singularity, where gravity is so strong that not even light can escape. In classical physics, if you throw something into a black hole, like a star, a gas cloud, or a spaceship, the black hole gains mass. And because the radius of a black hole is directly related to its mass, if the mass goes up, the horizon grows. That part is intuitive. But Hawking took it a step further. He looked at what happens when two black holes collide. These are the most violent events in the universe. When two black holes merge, they crash together and form a single, larger daughter black hole. In this process, they release a catastrophic amount of energy. We are talking about more energy than all the stars in the observable universe combined, released in a fraction of a second as gravitational waves. You might think that losing all that huge amount of energy would cause the final object to shrink or compact down. But Hawking's math said no. He proved that even with that massive loss of energy, the area of the final black hole's horizon must be larger than the sum of the areas of the two original black holes. Mathematically, the area final is greater than area 1 plus area 2. For decades, this theorem sat in textbooks as a mathematical jewel. It was widely believed to be true, but it was considered impossible to test. To test it, you would need to measure a black hole before and after a collision with extreme precision, something that was pure science fiction in the 1970s. But fast forward to where we are now, at the end of 2025. The universe finally revealed its secrets. This past September, the physics community was electrified by an announcement from the LIGO-Virgo-Cagra collaboration. 10 years after we first detected gravitational waves, and following a preliminary test back in 2021, scientists have delivered the gold standard confirmation. With the detection of a signal named GW 250,114, they have proven Hawking's area theorem with a staggering 99.999% statistical confidence. This is no longer just a theory, it is an observed law of nature. So how did they do it? How do you measure the surface area of invisible pits in spacetime from 1.3 billion light-years away? This is where the science gets incredibly cool. The key lies in how we analyze gravitational waves. When two black holes merge, the signal we receive on Earth has distinct phases. The first phase is called the inspiral. This is when the two black holes are spiraling around each other, getting closer and faster. By analyzing the frequency of the waves during this dance, physicists can calculate the mass and the spin of each individual black hole before they touch. From those numbers, they can calculate the total surface area of the two parents. Then comes the merger, the crash. And immediately after that, we get the second crucial phase, called the ringdown. Imagine striking a bell. After the initial clang, the bell vibrates or rings at specific frequencies before it goes silent. A newly formed black hole does the exact same thing. It is distorted and lumpy right after the collision, and it rings as it settles down into a perfect sphere. By analyzing the specific frequencies and overtones of this ringing, scientists can calculate the mass and spin of the new daughter black hole. And from that, they get the final surface area. The challenge has always been that the ringdown is very short and very quiet. In the first ever detection back in 2015, the signal was just a blip, a whisper buried in noise. We simply couldn't hear the ringdown clearly enough to be sure. But the detectors have been upgraded massively since then. The global network now uses quantum squeezing technology to reduce background noise. On January 14, 2025, a signal arrived that changed everything. GW 250,114 was loud. The signal-to-noise ratio was unprecedented. It came from the merger of two massive black holes, roughly 35 and 40 times the mass of our Sun. Because the signal was so clear, researchers could perform the inspiral versus ringdown test with surgical precision. Here are the numbers they found. Before the merger, the combined horizon area of the two parents was roughly 240,000 square kilometers. That is about the size of the United Kingdom. After the merger, the new black hole's horizon measured approximately 400,000 square kilometers, which is comparable to the size of Sweden. The increase was unambiguous. The area had grown, just as Hawking predicted. But why does this matter? If we already trusted Einstein and Hawking, isn't this just checking a box? Not at all. This confirmation is a structural pillar for modern physics, and it has profound implications for three specific reasons. First, it rules out the imposters. There are exotic theories of gravity that predict objects that look like black holes but aren't quite them. Things called boson stars or gravastars. These objects would not have an event horizon in the same way, and they would behave differently during that ring-down phase. If the surface area had shrunk, or if the vibrations were slightly off, it would have been evidence for these exotic objects. The fact that the data adhere so strictly to Hawking's law confirms that these really are the Kerr black holes predicted by general relativity. We are dealing with the real deal. The second reason this matters is the connection to thermodynamics. This is perhaps the most profound point. When Hawking and Jacob Bekenstein were working in the 70s, they realized a parallel. The second law of thermodynamics states that entropy, or disorder, in a closed system can never decrease. Hawking's area theorem states that the area of a black hole can never decrease. They realized this wasn't a coincidence. The area of a black hole is actually a measure of its entropy. This birthed the field of black hole thermodynamics. It implies that these dark voids aren't just gravitational pits. They are thermal objects. Validating the area theorem is effectively validating the Bekenstein-Hawking entropy formula. This formula is famous because it is the only place in physics where we see the constants of thermodynamics, gravity, relativity, and quantum mechanics all sitting in the same equation. By verifying the area side of that equation, we are confirming that we are on the right track toward a unified theory of everything. Now, I know some of you sharp listeners are thinking of a contradiction here. You might be asking, wait a minute, doesn't Stephen Hawking also say black holes evaporate? If Hawking radiation makes black holes lose mass and shrink over billions of years, how can the area theorem say they never shrink? This is the famous paradox, but the answer lies in the timescale and the type of physics involved. The area theorem is a law of classical physics. It governs violent, fast events, like mergers. It says that in these classical collisions, the area must grow. Hawking radiation, on the other hand, is a quantum mechanical process. It is incredibly slow. For a black hole of this size to evaporate would take longer than the current age of the universe. So are they contradictory? No. Verifying the area theorem confirms the classical limit. It sets the baseline. It tells us exactly how the black hole behaves according to general relativity, which allows us to look for those tiny, subtle deviations that quantum mechanics might cause in the future. We have to confirm the rule before we can find the exception. Looking ahead, this discovery opens the door to the future of astronomy. As we move toward 2026, we are preparing for the next generation of detectors, like the Einstein telescope and the space-based LISA mission. The clarity of the GW 250,114 signal has shown us that we can listen to the harmonics of space. Just like you can hear the difference between a violin and a piano playing the same note because of their overtones, we are starting to hear the overtones of black holes. Hidden in those faint harmonics might be the cracks in general relativity that we have been looking for, hints of the quantum structure of spacetime itself. But for now, the verdict is in. 54 years after a young Stephen Hawking scribbled a derivation in a notebook, the universe has spoken. We have built machines capable of listening to the shape of spacetime, and we have confirmed that the area of a black hole is an indelible record of its history, a cosmic ledger that, in the violent dance of gravity, can only grow. It is a monumental achievement for humanity, verifying a truth that was once just a whisper from the void. That is it for today's deep dive. We will be back next time to explore more mysteries of the cosmos. Keep looking up.